All right, cool. Hello, everyone. This is Team 7. This is our final report. We decided to analyze and redesign an exercise weight rack. Going to the product, the purpose of the product is to hold a barbell while providing stability and adjustable seating and facilitate different weightlifting exercises. On the left, we have an isometric view of our CAD model, and on the right, we have an exploded view of the different sub-assemblies of our exercise weight rack. Our primary customers would be commercial gyms and fitness centers, while our secondary customers would be residential individuals or families. Going to the functional analysis and the exercise, it would be able to facilitate exercise by supporting the user, hold the bar, guiding the weight, reduce openings. The exercise weight rack must also be able to change the incline and also add exercises, and also the user must be able to lie comfortably.
The function component mapping matrix lists functions and components. The functions are derived from the terminal nodes of the FAST diagram, which includes supporting user weight, holding weight bar, guiding weight, reducing openings, changing incline, having exercises, and lying comfortably. Components are from the leaves of the fishbone assembly diagram. The functional differentiation table shows the differences in functions between the two target customer groups. For the functions that are the same for both our groups are supporting the user weight, holding the bar, constraining movement, guiding weight, reducing openings, and lying comfortably, while the functions that are different for each customer group are changing the incline and adding exercises. The component commonality table simplifies the assembly into two categories, modules and platforms. Modules are components that take different forms in each product variant, which are the main rack subassembly, the height adjustment rod holders, the adjustment rod bracket, and the leg curl subassembly. While the platforms are the main rack subassembly, the bottom support subassembly, the seating subassembly, and the plastic cap. The left CAD model represents the commercial variant of the product, which is lacking the leg curl assembly and the incline adjustment components. The figure on the right shows the secondary customers segment, which includes the modules required for adjusting the incline, as well as the leg curl assembly, which adds exercises. The top left figure shows the adjustment bracket, allowing the user to adjust the incline of the bench seat. By tapping holes, as seen in the bottom left figure, from the bracket into the legs of the bench assembly time can be saved by eliminating the need for welding the brackets on. The center figure shows the main rack subassembly with the height adjustment module components, which can be attached onto the main rack platform, depending on which customer group variant is being assembled. The leg curl subassembly fits into the slot of the bottom support subassembly and then attached to it using a fastener as shown on the figure right.
This is our assembly sequence 2 corresponding to the second fishbone diagram. You can see that seating is the same for both, yet it occurs after differentiation, and this is bad, and we would like to eliminate that, which is why in assembly sequence 1, it is differentiated later on, putting the seating before it splits into the two different branches, which is what we want. In our design for manual assembly, the original assembly time and efficiency was 596 seconds and an efficiency of 0.06. For our redesign, we chose these parts because they performed important functions and had longer assembly times. We did this to reduce part counts, increase symmetry, and add features to facilitate their orientation. After the redesign, the time was 513 seconds and a 0.07 efficiency. You can see the changes that were made. The height adjustment bar holders became one part, and they were screwed, not welded, and an outline was put into the tall leg in order to facilitate assembly. The regular bar holder became a single piece with no welding necessary. It became easier to handle. The symmetry allows for easier assembly, and the countersinks make it easier to adjust using a screw bolt. In our design for automated assembly, the original cost of those 3 parts was going to be $1.34. These parts were important to redesign because they provide stability to the weight bench and are interfaces between different subassemblies. Cost after redesign was $8.25, and this cost reduction mostly came from changing the adjoining piece of bench assembly into one part rather than two. You can see in the upper left how the adjoining piece of the bench assembly was changed. The flat ground support was also changed, and the adjoining piece of the weight assembly was also changed.
For the height adjustment rod holder, since we are consolidating it into one piece, the overall size inherently grows. To align the part into the main rack assembly, the outline dimensions of 60 millimeters by 235 millimeters with an overall tolerance of 0.5 millimeters are critical. Other critical dimensions in this part are the locations of the holes. For the bar holder, again, the overall size of the port is critical to function as it needs to be able to fit into the top slot of the main rack assembly. The 68 by 28 millimeter dimensions are to allow it to fit into the slot with no interference and some buffer. The 1 millimeter tolerance will not interfere with the main rack, even in worst case and RSS scenarios, proving a robust redesign. For the height adjustment rod holder and the bar holder, based on the product specs such as material, shape, and batch size, we use the various process selection charts to narrow down the possible manufacturing processes. For the height adjustment rod holders, we recommend using die casting to produce a part as opposed to sheet metal working in the original design. For the bar holder, the recommended manufacturing process is machining as opposed to extrusion and sheet metal working along with the welding step in the original design. Comparing the redesigned height adjustment rod holder to the original, the material cost did increase by about 584% due to more material. However, the total number of parts did decrease. The machine operating costs also increased due to the size of the part and the cost of the die, along with the slightly different aluminum alloy which was used. So this increased the cost by about 281% per part. The big cost savings came from the assembly costs as this drastically decreased because there were less parts to handle, poke yoke features to aid in the placement, and the need for welding was eliminated, and the cost decreased by about 88%. Overall, the total cost of the height adjustment rod holder decreased by 77.5%. Comparing the redesigned bar holder to the original, the material costs increased slightly due to a different aluminum alloy used. It increased by only about 10% per part. The operating costs also increased due to the number of features in the machining steps and increased by about 20% per part. And again, the big cost savings came from the assembly costs, which decreased by about 86% because there was no need for welding. There was a symmetric design to aid in the placement, and the geometry is much easier to handle. Overall, the total cost using the analytical method decreased by about 2%. And then looking at the 3D Hubs cost estimation, the cost decreased by about 25%. So there are 4 factors to our product service system that will allow for customers to have opportunities to interact with the manufacturer and allow them to tailor their experience and costing. Without these systems, there's also a substantial negative impact on the environment. So first, we want to provide services such as delivery and setup and maintenance inspections. We also want to increase shared use by providing both customer groups the option to rent the equipment for a monthly fee. Lastly, since we are using recyclable materials, we will offer a return and recycle program for customers to send back any metal or plastic component for a discounted price on the new piece that they're replacing. So finally, looking at our redesign, the benefits were increased ease of manual and automated assembly, decreased overall cost of the parts and number of parts, and better delayed differentiation in the product family design. The pros and cons of our redesign include reduced number of parts and symmetric design, along with increased part size and increased manufacturing costs. If we were to start over and approach it differently, we would first identify components within the subassemblies that can further be modularized and also use stock materials in more areas to reduce manufacturing costs. Thank you for your time. We are Team 7.